Hi, everyone. We are speeding towards the finish line here. The last topic of the semester is going to be hypothesis testing. That means basically that we have something that we think is true, and we try to test that by taking a sample from a population that we are interested in. So we think something is true about that population. We formulate a hypothesis based on that. Okay, so that is something that we think is true. Then we take that random sample and we see if that either confirms to some extent whatever it is that we think is true, or if it seems to fly in the face of it. If it flies in the face of it enough, then we will reject that hypothesis. Okay, so that is the essence of a hypothesis test. And believe it or not, this is going to be rooted in the notion of a confidence interval, and the decision whether we reject the hypothesis or not is going to be based upon whether we happen to fall within a particular confidence interval, or if we're outside of it in the tails or something. Okay, and that will tell us that we are in something called the rejection region, and we will reject the hypothesis that we started out assuming at the beginning if it's too wildly out of bounds. Okay, so before we dig in here, I just want to mention to be on the lookout for the finals. I will send those out very soon, in all likelihood by tomorrow. So be looking for those. Of course, I will send out some kind of notification to let you know. And I anticipate giving you about a week to work on those, although the amount of time I expect that it will take you, or suspect it will take you, is probably more like 2 to 3 hours or something. So I would just caution you to plan accordingly. All right, so let's jump in here. Okay, so test of statistical hypotheses. And we're going to be focusing exclusively on the situation where we have a hypothesis formulated about the mean of a population. I will remind you of the picture that I've drawn over and over again of a population. We have parameters that we want to know things about in there, and the parameter might be mu or sigma or whatever it is. And then the sample that we take, we can get statistics from that, okay? Statistics that are point estimations of the parameters in question. And then we form confidence intervals from those statistics, okay? And we have a confidence interval for the population mean based on that sample. And again, if something is weirdly out of line with an initial hypothesis we had formulated, then we would tend to reject that hypothesis. And everything we're going to do is going to be involving thinking about some kind of population mean. But just know that hypothesis tests don't always have to be about means. They could be about variance. They could be about other population parameters, for sure. And you would just have to use a different distribution potentially. Okay, so here's the main idea. You use your sample. I already kind of said this, but just to repeat, you use your sample to test a hypothesis about a parameter, such as the mean or property of the population. Okay? For instance, I haven't said this before, but a property of the population would be something like, my hypothesis is that the population distribution is normal. It has the normal distribution. That is actually a hypothesis that you can test. All right, there are tests that will deal with that. It turns out it involves something called the chi-square distribution, which you may or may not have heard about before. Okay, and you make something called a contingency table, and you run something called a goodness of fit test to figure out if indeed that's a good hypothesis or not. You say, I think it's normal. And you do a goodness of fit test, and you decide whether you do not reject that hypothesis or you reject it based on the the data that comes back. A statistical hypothesis is a claim about one or more parameters of a population or about the type of distribution, like I just said. Okay, so here's some things that we might, hypothesize. So for instance, if mu sub m is the mean height of Cedarville men, and mu sub w is the mean height of Cedarville women, and we're going to say that this is like maybe in inches or something like that, then maybe I think that the difference between the mean height in inches for men and the mean height in inches for women is 6 inches. It's half a foot, okay? So that is something that I believe. It's kind of like my preconceived belief. And then what I do is I go and I gather data, a sample of men, a sample of women, and I kind of compute statistics from that, and I see if that statistical data comports with that hypothesis. Okay, if I went and I computed it and I ended up, getting a sample mean difference for men and women that was like, 0, then that starts to make me think that, oh, maybe that wasn't a very good hypothesis. So I probably should reject that. Okay, so the second one, the proportion of defective circuits produced by a certain manufacturer is less than 0.1, okay? So you could formulate a hypothesis test based on that, thing that you think is true. The distribution of ages in the US is normally distributed. That is a hypothesis you could test. It wouldn't be a test about one mean, but it would be a so-called goodness of fit test. Okay. All right. So how to formulate a hypothesis test? Well, you always have 2 things going on. One is called the Null Hypothesis, and you notate that H sub 0. Sometimes you say H naught, okay, or you just say the null. Some people even say ho, okay, they say ho for the Null Hypothesis. And then you have the opposite of that, which is the Alternative Hypothesis. You denote that by H sub A for the Alternative Hypothesis, okay? And sometimes you call these the ho and the ha, okay? And the Alternative Hypothesis is contradictory to the null, okay? So it's either this or it's the other. Okay? And again, the null is kind of your prior belief claim. So this is kind of the thing that you're starting with is your baseline assumption, okay? The Null Hypothesis is the thing that you start with. You kind of start by assuming that, and you do all of your computation based on that assumption. The Null Hypothesis is rejected in favor of the Alternative Hypothesis if sample evidence suggests that the null is false. So if you get some kind of like very unlikely thing happening under the assumption of the null. Okay, you assume the null, you do all of your computation with your sample based on that, and if you get something that is very unlikely based on that assumption, then you will reject it, and we'll make all of this rigorous later. If the sample does not strongly contradict the null hypothesis, then you just continue to believe the null, okay? And the Null Hypothesis is favored, meaning that we sort of stick with the Null Hypothesis unless there's a lot of evidence that is, false, contradictory to the assumption of the null, okay? Be careful about some of the language that you use here. You don't ever say that you accept the null as absolute truth. There always exists the small possibility that the sample you got was just an unlikely sample. So you don't ever say, I 100% reject the null and accept the Alternative Hypothesis. You don't say it like that. You just say, you reject the null. Okay, you think that that's unlikely to be true, or you say we do not reject the null, which means that it's there isn't enough evidence to reject it, and so we're going to continue to believe it. But there's always that outside chance that you could be making a mistake. Okay, that's just the nature of statistics. So the null hypothesis is generally the hypothesis that corresponds to no change from current opinion, okay? No difference, no improvement. It's just equal to whatever it was before, okay? The null hypothesis always includes equality, okay? So that's something to bear in mind. It always includes equality. And depending on the statistics text you look at, it always includes equality, but sometimes it will involve like greater than or equal to, or less than or equal to, but there's always an equals on the null side of things. The way that I'm going to develop it here, the null is always going to literally have an equal sign in it, okay? And we're going to say, look, this is how we're always going to proceed. Because it turns out that when we do our computation, we are always going to assume the null hypothesis and work from there. Okay, so I already kind of said this, but we can reject the null, or we can fail to reject the null, but we do not accept the null or the alternative hypothesis. Okay, we don't ever say accept. We either reject the null, and we kind of start to think that the alternative hypothesis is more likely to be true, or we fail to reject the null. Okay. So one of the classic examples to illustrate what's going on with hypothesis testing and the way in which it is set up is the US justice system. Okay. So you always start in the US justice system, you always start by assuming something, okay, at the beginning. And what is it that we always say with the US justice system? We say that you are innocent until proven guilty, right? Until the evidence becomes so compelling that you have to reject that hypothesis and revert to the opposite one, the alternative hypothesis, which is guilty. So you start under the null hypothesis that the person is innocent. So you kind of assume they are innocent until proven guilty. So you work under the assumption of innocence until the evidence becomes so compelling that that no longer seems like a rational thing to do. Then you reject the null and revert to the alternative, namely guilty, okay? So the null is innocent, the alternative is guilty, okay? And we'll return to this example later on when we talk about the sorts of errors one can make, the sort of errors that one can make when you're doing hypothesis testing. And essentially why it is that we set up a hypothesis test this way. Turns out that one kind of error is seen as much more egregious than the other type of error. Okay? And we'll talk about that a little bit in just a few minutes here. So here's another example. From repeated testing, a company knows that the mean lifetime of a certain product is 1,000 hours. Okay, so that means population mean is 1,000. A researcher in the company wants to introduce a new design that the researcher believes will cause the product to last longer than 1,000 hours. Okay. So what would the null hypothesis be? Well, the null hypothesis would be that nothing changes, okay? Like in this example, you kind of believe that the mean has increased. So here, kind of what you believe is the alternative hypothesis, namely that the population mean mu, the new mean mu under this new design is bigger than 100. But the null hypothesis always has equals in it. So you kind of set up the null as mu equal to 100. You call this the prior belief claim, and we always work under that assumption. But it's okay that sometimes you actually are believing the alternative hypothesis. Okay, but you always put equals on the null, and that's kind of the assumption that you start with when you're assuming. Or you start with assuming the null, you work with that, and then if evidence becomes too compelling to accept that anymore, you reject it and you revert to the alternative. Okay, so this is how you would set this up. Okay. So this is like the general situation that you might run into. So there are three situations you might run into. And by the way, theta is just, right, so that's the Greek letter theta, okay, just so that you know. Let me kind of get in here and write this. So theta, right, this is the Greek letter theta, okay? And this is theta, this is theta sub 0 or theta naught, okay? Some specific value like 1,000 or something like that. So here you have the alternative hypothesis is that theta is bigger than theta naught. Then of course, the null would have to be theta equals theta naught. Okay, and I'm saying not right here just because it turns out in the literature more often than not, this guy right here is never used. The null hypothesis is usually set up this way. Okay, so again, it just depends on the text that you happen to be in. Okay, but we always kind of put equality in the null, the way that we're going to be doing this, and the way that it tends to show up in literature. But it technically wouldn't be incorrect to do this one also. But this is the one that we're kind of gravitating toward here. Okay. The second one is, the alternative is theta is less than some specific value. Then again, the null is still theta equals theta 0. And then there's a third possible way to set it up, namely theta is just different from theta 0. It's either below or above it, but it's definitely not equal. And again, the alternative being that, the null again would just be theta equal to theta 0. Okay? And again, theta is just some generic parameter. Theta 0 is a specific value of that thing. Okay? And you always start by working under the assumption of the null. Do everything based on that assumption and see if it leads towards something that's reasonable or not. Okay. So for each pairs of hypotheses, state whether they comply with our guidelines and why. All right, so is number one okay? Well, the null has mu equal to 100, and the alternative is that mu is greater than 100. Yes, that would be okay. All right, so that would be an okay thing, right? You have equality in the null, and you have a strict inequality in the alternative. Okay, remember, if I go back here, you either have a strict inequality or just not equals. Those are the possibilities for the alternative. Okay, what about the second one? Well, the second one, you have equality for the parameter sigma, but this right here is not allowed. Okay, you can't have equals in the alternative. It's just got to be strict inequality. So this is no good for that reason. Okay. The null being p different from 0.25 and the alternative is p is equal. No, that's no good. These guys would have to be switched in order for this to be a valid setup for a hypothesis test. Okay. What about mu1 minus mu2 equal 25? And the alternative, mu1 minus mu2 greater than 100. Yeah, that'd be fine. Okay. Okay, what about, S1 squared equals S2 squared? An alternative is S1 squared doesn't equal S2 squared. Now, I'm not so sure what S stands for. That makes me a little bit nervous because I can't, I don't really know. But if by S you meant like, sigma, that might be okay. So I'm going to put a little question mark here and just say that we need to have, right, and I'm going to say that we need to test population parameters. Okay, so we don't ever formulate our hypotheses, null or alternative, based on actual sample statistics. We formulate them based on population parameters. Okay, and then we use the statistics to test whether those are reasonable. The null hypothesis is a reasonable thing to be operating under. Okay, I'm inclined to say that this is a no, but if indeed S1 squared or an S2 squared represents some kind of population parameter, then we would be okay. Okay. All right. So a test statistic is a function of the sample data on which the decision to reject the null or fail to reject the null is to be based. Okay, so we might, the test statistic might be X bar, the sample mean. And it will be X bar if indeed, if indeed we're trying to formulate a hypothesis based on the population mean, which makes sense that the sample mean would be involved. And in all likelihood, the sample standard deviation would be involved also, because we would probably try to convert things to z-scores, okay? A rejection region is the set of all values of the test statistic for which the null will be rejected, okay? So you have your test statistic, and you kind of set up a rejection region, and if the test statistic falls into that rejection region, boom, you reject the null, and that's the conclusion of your hypothesis. Reject the null, you would say there appears to be enough evidence to reject the null, and it would seem that the alternative hypothesis is likely to be true. Okay, but that's not the same thing as saying that you accept it. You just say, based on these data, seems like the null is unlikely to be true. Okay. All right, so this is that thing I was talking about, namely type 1, or the types of errors that you can make when you're doing a hypothesis test. The first type you can make is a type 1 error and a type 2 error. And I always like to draw a little box here. Okay, so I'll draw a little box. Okay, so let's say, this is, that the null is true or the null is false. Okay, the null is either true or it's false. Okay, and then what are the two things that you can do with the null? Well, you can reject the null or not reject the null. Okay, so that's labeling our columns. So you tell me which, well, I have to tell you, I guess, which of these boxes are actually erroneous. So if the null is true, so like the upper left box there is the null being true, and we reject the null. Okay, the null being true and we reject the null, that is a mistake, okay? That's not good. The other type of error, okay, so by the way, what if we rejected the null when the null was false? Well, that's good. Say, I'll put a check mark right there, okay? And what if the null were true and we don't reject the null? Well, then that's good also. And the other type of error we can make is if the null is false and we don't reject the null, okay? So those are the erroneous zones when we set up our hypothesis test. So what is a type 1 error? Well, a type 1 error consists of rejecting the null when it is actually true. So this is a type 1 error right here, okay? All right, a type 2 error consists of not rejecting the null. So not rejecting the null when the null is actually false. That's a type 2 error, type 2 error. Okay, type 1 error should always be the more serious error, okay? And we're gonna associate a number to this, and we'll call that alpha. And to the type 2 error, we associate a number that we call beta. Okay, and alpha is the thing we're gonna wanna control because that's always the more serious. Turns out when you set these up, you can really only control one of these types of errors. Okay, you can control the percentage of time. That's what alpha is going to be. You can control the percentage of time that you make the type 1 error. Okay, so you want that to be very small. Okay, so for instance, I mean, so let's return to this jury situation. Okay, type 1 error occurs when an innocent person, okay, so type 1 error occurs when an innocent person, because remember, what was H0 in that case? So H0 we assume that they are innocent. And what is the alternative hypothesis? Of course, that means that, if you reject the null, then you're convicting them, okay? So type 1 error occurs when an innocent person, okay, so that means that H0 is true, is declared guilty. So that means you convict an innocent person, okay? You reject the null and they're declared guilty when in fact they are innocent. A type 2 error occurs when a guilty person, okay, a guilty person, so the null is false, right, is declared innocent. So they are acquitted, right? They are acquitted even though they are guilty. So that's an error, okay? Which of those two do you think is more serious? Convicting an innocent person or acquitting a guilty person? Well, I mean, we might quibble about that a little bit, but it does seem like that convicting an innocent person is more egregious. So that's the one you would want to control, okay? So that's why we really kind of hone in on the type 1 error. We want to control the percentage of time that happens because that's not good at all, okay? Type 1 error is always more serious than the type 2 error. This can help you choose the null and alternative hypothesis, okay? So that's how you can kind of control, how often you're making the type 1 error is by sort of formulating null and alternative hypothesis appropriately. Most of the time, what you do is you kind of put, like for instance, in that case we were talking about earlier with, some product that you had that was averaging 1,000 hours of life before, okay? The null hypothesis is, that the mean is still 1,000. The alternatives is greater than 1,000. Okay. So, and whatever conclusion you come up with is going to dictate what you do moving forward. So maybe even changing the whole production paradigm based on this test. Okay. So, what if you fail to reject the null? Okay. If you fail to reject the null, when in fact it was the case that the mean had increased, then you would just continue with the status quo. You wouldn't necessarily change your whole production paradigm, and that you would make that error, but that doesn't seem too horrible. But the other type of error in that case, namely that the mean really is 1,000, like there was no improvement at all. If you reject that and start producing under a new paradigm, you might spend millions redesigning the production lines and things like that when in fact the mean hadn't gone up at all. Okay, that's a horrible thing to happen. Okay, so you would want to control that error. That would be your type 1 error in that case. So that's another kind of off-the-cuff example that shows that the alpha error is far more serious. Type 1 error is far more serious. So that's how you kind of set up your hypotheses. Before agreeing to purchase a large order of polyethylene sheaths for a particular type of high-pressure, oil-filled submarine power cable, lots of words, a company wants to see conclusive evidence that the true standard deviation of sheath thickness is less than 0.05 millimeters, okay? Conclusive evidence that sheath thickness is less than 0.05 millimeters. What hypothesis should be tested and why? In this context, what are the type 2 and type 1 errors? So let's think about that for a minute. Well, seems like the only really reasonable assumption here would be that the null would simply be that sigma, right, the standard deviation, is straight up equal to 0.05. And the alternative hypothesis would be that sigma, now look, we want conclusive evidence that the sheath thickness, the standard deviation of the sheath thickness is less than 0.05 millimeters. So we don't want, remember, standard deviation measures variability. So we want very small variability before we take the leap and purchase these things, okay? Purchase this large order of polyethylene sheaths, okay? So it's going to be sigma less than 0.05, okay? What would the type 1 error be? Okay, well, remember, type 1 error means that you reject, that always is that you reject the null when true, okay? And type 2 error is always that you do not reject the null when it's false. Okay, do not reject the null when it's false. Well, what would that do? What would that cause us to do in the first case? Okay, again, so the type 1 error, first of all, remember, we have a number that we'll associate with that called alpha, okay? And then for the second type, we'll call that beta. But what will these cause us to do? If I reject the null when it is true, okay, then what's going to happen? If I reject the null when it's true, then I'm going to think that the alternative is true, right? That's the thing I'm going to be leaning toward. And so I'm going to make this big purchase, okay? I'm going to take the leap and actually make this big purchase. Okay, what if I do not reject the null when it's actually false? Okay, well, if I do not reject the null, then I'm going to still believe that the sheath standard deviation is 0.05, and I won't make the purchase. So this is no purchase. Okay, which of these two is more egregious? Making a purchase that was actually a bad idea, or just not making a purchase that could have been a good idea? Well, clearly, I hope you think it's clear that making the purchase, this is far worse. This is really bad, okay? Which is why you always want to control that type 1 error, that alpha error, okay? And again, alpha is going to be the percentage of time that you make that error, okay? And beta is the percentage of time you make the type 2 error. But again, you can only control one of those, as we will see. We always opt to control the type 1 error because it's always worse, okay? All right. So next example, let mu denote the true average radioactivity level in picocuries per liter. The value of 5 picocuries per liter is considered the dividing line between safe and unsafe water, Would you recommend testing mu equal to 5 versus mu greater than 5, or mu equal to 5 versus mu less than 5? Which of those two do you think would be the one that you would want to use as your hypothesis test? Well, it seems fairly clear. Okay, so where mu is like the mean picocuries per liter level. Okay, and then you would take a sample, a random sample. Okay, several samples of water, maybe compute the sample mean, and then you would formulate whether or not to reject the null or not. The null is always going to be mu equals 5 here. That's the dividing line. But the only time you would want to reject the null in favor of the alternative is if indeed it's to our benefit. Okay, so that is, we have safe water here. So it seems clear that this is the one right here that we should opt toward. That is, we only want to reject it if it looks like the mean is actually smaller than that. Okay, and so we're going to revert to actually concluding that the water is safe if we end up getting a sample that's really far below 5. Okay. Right, because what would the type 1, okay, so let's think about that. What would the type 1 error be in this particular case? Remember, that means that we would reject the null when it's true, okay? So I would reject the null when it is true, okay? So what would that mean would happen? So that means that you would be drinking unsafe water, right? So you would conclude that the water is safe when it's not, okay? What's the type 2 error? Okay, so you do not reject the null when it's false, okay? So what would you do? So you would conclude that the water is unsafe when it is. Which of those two errors seems worse? Well, I hope it's clear to you that it would be this one. So this one would be really bad, once again, right? So this is, so it makes sense, once again, why this would be the one that we would want to control. That's our alpha error. Okay, concluding the water is safe when it is, you won't drink it, so you won't harm yourself, even though it's safe. I mean, that's not that bad. But concluding that the water is safe when it actually is bad, that's a bad thing to do, because you would be drinking unsafe water. Okay, so once again, we see that type 1 error is the thing that we would want to control. Okay, moving on. So alpha, which is the type 1 error, that's called the significance level. And that is the thing we are going to want to control. And beta, and again, alpha is the percentage of time we make that type 1 error. Beta is the percentage of time we make the type 2 error. And that's oftentimes referred to as the power of the test. The power of the test. Okay. And here are some steps. We're not going to actually go do some test statistics in this lecture. This is just a setup for the philosophy of hypothesis testing. But here's the steps that you go through. And hopefully we've already kind of articulated every bit of this. And I just want to have a place where we've listed all these. Okay, so first of all, you identify the parameter of interest, be it the mean, population standard deviation, or variance. Could be anything else that's something you want to know about the population, even the distribution of the population. You state the null hypothesis. You state the alternative hypothesis. You set that thing up. And then you write the formula for the test statistic, okay? So you're going to gather a sample. You state the rejection region for the chosen value of alpha. Now remember, alpha is making the type 1 error. That's what you're going to want to control. And again, the alpha here is exactly the same as the alpha we were using over in the confidence interval stuff. Use the exact same letter for good reason. It's the same thing. Okay, sometimes you'll set alpha to be 0.05. So that is the percentage of time you're willing to make the type 1 error, which is usually the more egregious error. Okay? And again, it's not easy to compute what beta is. Sometimes you can do it, other times it's just not very clear. Okay? But generally speaking, if alpha is small, beta will be small also. Compute the necessary sample quantities, okay, like X bar, for instance, and substitute that into the test statistic. Okay, so maybe the test statistic will be something like X bar minus mu over sigma divided by square root of n or something. Okay, and you simply substitute in what X bar is, or maybe instead of sigma, it's like S or something. Maybe you compute X bar and S and you plug it into that test statistic and you see what kind of information you get, whether you land in the rejection region or not. So decide whether the null should be rejected or not. And the way you make that decision is based on whether the test statistic falls in the rejection region. okay? So that's kind of the general rubric that you go through when you do this. Now, when you go read academic papers, even in like nursing or in the medical profession in general, they set up the null and alternative hypotheses the way that we've done it, where the null is always an equals, the alternative is always an inequality or a not equals, okay? And then they usually, instead of actually stating a rejection region, they'll state something called the p-value, okay, the p-value. And you know, based on the test statistic, they'll get a p-value for that, and they'll compare that to like alpha, and they'll make the decision based on that. But it's really the same thing. It's just stated differently, and we'll see the p-value situation and how it really is the same as the rejection region, and we'll explain that later on. I just want to go through this one slide. This is at the halfway point of this stuff. I'll go through this one slide, and we won't get into any examples here, but this is basically one way to set this up, and I'll kind of repeat this next time, but I just want to prime the pump for what's going to happen. Okay, so we'll go through a similar number of cases that we had for a confidence interval. That's not surprising, because I said that all of this is rooted in the ideas and concepts we were doing over there. Okay, so the assumption here, remember in case one, is that basically you have a normal distribution, and you know, you may have reason to believe that's true. And we know sigma, okay? This means that if H0 is true, okay, the null is true, namely that mu is equal to like mu 0, then x bar minus mu 0 over sigma x bar, which is, remember, sigma x bar is just sigma over the square root of n. X bar minus this, you know, null hypothesis mean mu 0 over sigma divided by square root of n, that's going to have the standard normal distribution. So if the value of that test statistic, that is the test statistic right there. Okay, so here's the test statistic. Test statistic. If the value of that test statistic is very large or very small in the standard normal table, then we know that x bar is far away from mu 0. Okay, if that happens, then you start to think, what is going on here? This suggests that mu 0 is not the correct value of the mean. Okay, because if I end up way off in one of the tails of what, you know, of the standard normal distribution under the assumption that the mean is mu 0, you start to suspect that something's weird. You would suspect more if mu 0 was the mean, you would expect to kind of be in the middle somewhere. You wouldn't expect to be way off in one of the tails. So this would suggest that mu 0 is not the correct value of mu, so we would reject the null, okay? So this is just kind of a general philosophical setup for what we're going to be doing. We'll do lots of examples. Hopefully this stuff makes sense just in terms of the philosophy of it. We'll even see how to go back and forth between a confidence interval and a hypothesis test. And yeah, we'll come back and talk about some of that stuff on Friday. I will see you then.